Hello, I hope you're well, Sackville. Welcome for our third instalment. I hope you managed to make it today. I know there was some confusion over the link, but let's see how many we get in today. So today's job is units, numbers, and characters. There's quite a lot to cover, but it's one of these areas in sort of Unit 1 where you can really pick up some marks quickly. So I can see there are a few of you are here. Excellent. Please do introduce yourself. Say hello in the comments. Be nice to welcome you. Be excellent to welcome you. I'm going to try not to cough all over you. I'm struggling a little bit with my coughing today, but let's get into it and let's crack on. Okay, so first of all, I'm going to jump back a few slides. First of all, just bear with me a second. Let's go back to here. Units, characters, and numbers. Now, actually, these don't all strictly go together. Two of them do, one of them doesn't. But I think it actually works quite well together because they all cover the same sort of area. So let's have a look at what we've got. I want to start off by having a little look back at stuff we've done before, so that we can just reflect on some of the stuff that we did with system architecture. So here we go. Here's the question. This is the answer to the question. This is an exam question. This is the answer. More RAM, more PC performance, speeds up access to data, excessive use of something can cause disk thrashing. What's the VM? What's this about, this question? Which decreases performance? VM. What's VM? Slower to access than RAM. Moving data between RAM and VM takes processor time. Any ideas what this question may have been about? Any ideas? Well, no one's jumping into it. It's a tricky one. This one often pops up. It's a memory question, and this one is, of course, the VM refers to virtual memory. So what are the benefits of having RAM rather than virtual memory? We've got two people here. One of them, say hello. Even got a like. Just say hello. Okay, next question. Let's have a look back at some quiz questions from last time. Actually, the first one is, can anyone name any memory registers? All two of you here, can you name one of them? Any of the registers that came that are part of the CPU? There are 4 memory registers that you need to know. And they love to open with this. So if you can absolutely nail the start of the exam with getting these 4 right, that would be a really, really, really good place to go. We've got 3 people in now. Go on, someone introduce yourself and say hello. It would be fabulous. I'm going to push forward rather than waiting for answers. So these are what the memory registers do. One stores the address where data will be read, and the key takeaway there is that you've got this idea of address here. So one's to do with an address. Another one is to do with data. And this one is the result of a calculation. And this one is the next instruction, the address of the next instruction. Those key words tell you what this is all about. Oh, excellent. Look at this. We have people here. Hello, Connor. Nice to see you. Well done for making it. Hello, dear man. Yeah, data register. That's excellent. Which one is the data register? We've got a data register and we've got an address register, okay? So, and I'm going to try and tease a bit more out of this. We've got 5 now. Excellent. I'm going to tease a bit more of this out of you next week and the week after, okay? So these are the 4 that you need to know. And if I show you this often enough, by the time we get to week 4 and week 5, you'll go, oh yeah, the accumulator. Oh, that's the one that stores the results of calculations, okay? And that's part of the arithmetic logic unit, which does math sums and it does logic, greater than, less than, not, is, and that sort of stuff, okay? Then we've got the program counter down here that points to the next instruction. And then we have over here the memory address register. And notice, right, in the von Neumann architecture, what made it different, John von Neumann was the guy who invented this architecture, the one that we still use today, because he did something that was unusual, which was to separate out these two, address from data. So the where is different from the what. It's held in a different place. It's treated differently, okay? It's used it's held within a different register. So that's what makes the von Neumann architecture so sort of unusual. All right. So let's jump in and have a look at what we're going to do today. And we're going to look at units of storage, denary to binary, adding binary numbers, converting denary to hex, binary shifts, size of text files, binary coding characters, and what characters are all about. It looks like 7 people in. This is good. Do say hello. Don't be scared. And if I say anything, I mean, I was talking last week and I was talking about the OS. And some brave soul said, what's an OS? It's an operating system. So don't forget, the premise of me being here is that I'm here to help you as an extra tutor for your computer science. And all of the material that I've covered, I'm going through the specification in order from point 1 right through to the end, okay? So all of the recordings are on the YouTube channel that you're on now. Just have a look at the Sackville playlist that's there for you. And of course, I update that each week. And each week I put in some chapter headings so you know exactly where to go to find the part that you're struggling with. Right, so that's the plan today. It's an ambitious plan, but I know that we can do it. So let's crack on with this. 20 minutes each. First question. You're sat in the exam, and at the very start, they're going to ask you, why do computers use binary? And you come up with a very, very formulaic answer to this. This will definitely be there in some form. So these are the sorts of answers that you can give. So why do computers use binary, which is ones and zeros? And in fact, it just equates to electricity flowing or electricity not flowing, or less of it. And that gives you 2 states. So computers are made from transistors and circuit boards, okay? And the components within these circuit boards have got 2 states, on and off, current flowing or current not flowing. And so therefore binary is the best choice of language to represent that, because binary's got ones and zeros. So look at how many marks there are for the question. If it's 1 mark, you can say that the components inside computers have 2 states, on and off. And then if there's 2 marks, you can say we've got 9 people in. You can say that's easily represented in binary because binary also has 2 states, 1 and 0. Okay, so that's why computers use binary. Do you know what? This is guaranteed to be in there. So make sure you've got an answer for that one ready to go. All right. This is a horrible phrase, units of data storage capacity. And it's just worth thinking for a minute that we are simply talking about where you store stuff. Okay, so if you store stuff on your phone in the hard drive or the solid state drive on your phone, you are storing units of data storage capacity. So we'll get into bits, bytes, megabytes, etc., because I think they're going to do quite a big question on that this year. Not that I have a crystal ball, but they didn't do much on it in the last exam. So I think that this one is overdue, and they'll make you do a bit of simple maths with this. The good news is you probably know most of this. So this is thinking about from smallest to largest. So when you store data, what's the smallest unit of data storage capacity? Well, it is, whoop, gone the wrong way. Let's try again. Well, it is the bit. So the bit has literally got 2 slots. And I keep saying slots because it is a slot in which you can store things. You can store 1 number in that slot, for example, okay? So bit, which stands for binary digit, can either contain a 0 or a 1, nothing else, okay? It can either be on or off. That's the only purpose that it serves. Then you've got 4 times bigger than a bit is a nibble. I've done it again. 4 times bigger than a bit is a nibble, which is here. And incidentally, hexadecimal numbers, 5D, 4F, each of those is a nibble, okay? So then you've got your byte, which is 8 bits. That's the hard bit. If you can master this part here, you're done. So that's where things are a bit hard to remember, that you've got 4 bits and a nibble, and you've got 8 bits and a byte, and you've got 2 nibbles and a byte. So you may have to do some maths involving dividing by 8 or timesing by 8 usually. They might give you things in bits and make you scale it into kilobytes or megabytes or gigabytes. Or they might give you a kilobyte or a megabyte and make you put it into bits. Okay, they may do. It's more likely that they'll make you scale up though. So once you've done this first part here, which is where we've got bits, nibbles and bytes, it's then easy because everything after that, look at this, everything after that is thousands. So as long as you know which order they're in, and most of you do, kilobyte. A megabyte's 1,000 times bigger, a gigabyte's 1,000 times bigger than a megabyte, a terabyte's 1,000 times bigger, and so on. So each of these are 1,000 times, oops, let's go back to there. Each of these, let's try again, is 1,000 times bigger than the one that came before it, okay? 1,000 times bigger, 1,000 times bigger, 1,000 times bigger. So your maths may involve some 8s at this early stage here, but it's more likely, so you might have some 8s to divide by there, but the chances are you're going to end up simply multiplying, sticking lots of zeros on the end. 3 zeros, 6 zeros, 9 zeros, and so on. That's most likely what they're going to get you to do. It's really worth just doing a bit of practice, making sure that you can do some simple. So make sure you can divide by 8. Make sure that in exam conditions you can do it. And don't forget, you can't use a calculator, so you are going to have to actually work that one out on the page. But it's not too bad, is it? It's not too bad at all. All right. So we're now going to look at 3 number systems, and they are binary, denary, and hex. Well, we're not going to look at denary, because denary is ones that you're experts on. That's decimal, the one that you use all the time. But the reason I'm drawing your attention to it is because of something weird that you've got used to, which is we don't ever count to 10, we count to 9, and then we go to 1, 0. So you've got 1, 10, and then you start counting again. Now, I know you're thinking, yeah, okay, thanks, mate, I know how to count to 10. But the point is, you have got used to the inherent weirdness of it. You're thinking, well, no, but you count to 10. You don't. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You get to 9, and then you say 1, 10. And then you go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, and so on, okay? That is quite helpful when it comes to thinking about hex and when it comes to thinking about binary as well, okay? So let's have a quick look at hex. I know with binary you know that it's zeros and ones, but hexadecimal goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but then it goes A, B, C, D, E, and F. And the reason I gave you, we've got 10 in, do say hello. The reason I gave you all that waffle about decimal being 1, 0 is that you don't get as far as G. You're thinking, but hang on, hexadecimal's 16, isn't it? But then once you go back and you've got 1, and you start 1, 0, that's 116 and no units, okay? 1, 1 is 116 and 1 unit, which is 17. Yeah, hopefully that'll start to make sense. I actually find the best way of doing this is to look at some binary, just written out, counting 1, 2, 3, 4, 5 in binary, and you'll have a moment where you go, oh, okay, just that light bulb moment. But you've got to spend a bit of time with it just to look at it to understand it, because it isn't as weird as it seems. Okay, bit of a stifled cough there. So binary conversions, easy. So let's jump into these. The job in hand is this, ladies and gentlemen. We are going to convert this number over here, which is 10101010, which is in binary. How do I know it's in binary? Because you've got that little 2 just there, okay? That means that it is in binary. Good. Right. So we're going to convert this binary number, 10101010, into denary. What do you need to do? Now, those of you who are half decent at maths will say, well, I don't need to do anything. I can just work it out in my head. And you're probably right. But there's quite a strong correlation between those who work it out in their heads and they end up getting one figure wrong. So given that you've got time to draw this grid, this is what I'd recommend that you do. Number 1, draw the grid. The difficult thing with the grid is notice that it goes from right to left, okay? That is a weird thing. It's a bit like writing in Arabic, because they start from the right and they go left. Whereas in Europe, or in Britain and Europe, we start on the left and go to the right. That's the first slightly unusual thing about it. After that, it's actually quite straightforward. As long as you start with the number, whoops, let's not do that. As long as you start with the number 1, you then just got to go across and double it. Double 1 is 2, double 2 is 4, double 4 is 8, 16, double that 32, double that, and then you get to 128, okay? That is literally all that you've got to do. And once you've done that, the maths then is a piece of cake. So number 1, if you're asked to convert from binary to denary, draw the grid. Right to left, 1, 2, 4, 8, 16, 32, 64, 128. You won't be asked to draw a bigger number than to go larger than 128. And by the way, just in case you're wondering, when I start talking about bits in a minute, 10 people in, do say hello, is that each of these is a bit. 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you can count through these different bits. So each of these bits, they are a unit in which you can store stuff. All right, let's jump on with the job in hand. So we're going to convert this number into binary. So you've drawn your grid. Next thing is drop those numbers into the grid, which I've done 10, 10, 10, 10. So far, no big deal. Here comes the magic. To work it out, you've then got to scan through the bottom half of the grid where you've dropped your number in. And you're going to focus on these numbers, but only the numbers where a 1 has been inserted. So that's here, 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 and here. Okay? You can ignore the zeros. We're not even thinking about those. So now, where you see I've put a square around them, where you've got the square, you go up to the top and you add that number, 128, to the next number, which has got a 1 by it, which is 32. Any of you quick mathematicians working this out before me? So 128 plus 32, quick maths, plus 8 plus 2. What do we think? I'll work it out really slowly. So we've got 128 plus 32. So I'd say that's 130, plus 30 is 160, plus 8 is 168. Any ideas what the final answer might be? You might be lagging quite far behind me because the weather's so awful. So I will crack on. If you don't understand this system I've gone through here, ask me, I'll go through it again quite gladly with you, okay? So you end up with a total, and the total, once you've done all of that, is in fact 170. So that's the way that you can convert from binary to denary. Draw the grid, drop the numbers in, where you've got a 1 in the bottom, find that, look up, find the number above it and add it to the next place where you've got a 1, add it to that, next place with a 1, add it to that, and so on. I mean, it couldn't be easier. There could be 1 or 2 marks on that for you in the exam. Easy as you like. Right, let's go on to the next one then. So this is now, we're doing something a bit different. So rather than going from binary to denary, we're going from denary. And how do we know it's denary? We know it's denary because you've got 170 with a little 10 there. So that's base 10, denary. That's the number system that we use. So we're taking 170 and we're going to convert it into binary. The great thing is, it works exactly the same. The first thing you do is that you draw the grid. And you draw the grid, okay, like that. Exactly the same thing again. 1, 2, 4, 8, 16. Okay, once you've done the grid, then we've got a slightly different approach to filling it, okay? So you ask yourself this question, and then you repeat the thing over and over and over again. So you ask yourself, and this is the question down here, what is the largest grid number? And when I say grid number, I mean these numbers on the grid here, okay? So those numbers. What is the largest grid number that goes once into our number here, okay? What's the biggest number that goes once into 170? And the answer is, of course, it's 128. 128 goes once into 170. Easy peasy. So guess what? You then simply draw a 1 in there. Now you've got some maths to do. Because 128 goes into 170 once, how much is left over? Well, it's 42. Because quick maths would say that it's 2 to make 130, and then 130 to 170 is 40, so it's 42. And notice that I've written down the word mod there. Mod is another way of expressing remainder. So if you're writing in pseudocode in paper 2, use the word mod. There were 2 marks for mod in the exam this year. And again, you pick up these, suddenly you've got a grade boundary. Learn those different registers for the CPU. And suddenly you're really picking up marks all the way through the paper. And this, for most of you, will be the case of rather than picking up 2 out of 5 or 3 out of 5, picking up 4 or getting 3 rather than 2. If you do that on enough questions, suddenly the grade 3s and 4s becomes grade 5s and 6s. The 6s and 7s become 7s and 8s. And that's the way that you can really pick up the speed. Anyway, back to the story, where we've got a remainder of 42. Well, guess what? You ask exactly the same question again. What is the biggest grid number that goes once into our 42? Because you've got 42 left now. You've got 42 still to deal with. So 32 goes into 42 once, and guess what? The remainder is 10. You find most of the maths is actually quite straightforward. Remainder's 10. You guess what the next question is? What is the biggest number of our grid number that goes into 10 once? And the answer is, it's 8. What's left over after you've taken the 8 away? We're resolving it here. What's left over? 2. You can see that's the mod. Okay. 8 goes into 10 once with 2 left over. So guess what? And notice you're putting a 1 in each of these places. It goes once into 128. It goes once into the remainder. This one goes once into the remainder, the biggest number. We've only got a 2 left. So guess what we're going to do? We're then going to draw a 2. We're then going to put a... I don't want you doing that. Go away. We're then going to put a 1 in the 2. And at that point, there's no remainder, so we have finished doing our sums. We have got 13 people. Do say hello. And well done for joining it so late. This was a bit of a mix-up, I think, about the link today. But well done for being here. So guess what you do with all these remaining gaps? Well, you're not going to put a 1 in there because we've already done that. So guess what? You put a 0 in there. And that's how you fill it out. You just fill in all the blanks with zeros. And that is how you convert a decimal, a denary number, into a binary number. Easy peasy, isn't it? Simple as you like. Go back and practice a few. This is guaranteed to be in there. I don't think they've ever done an exam without some binary conversion being in there. Sometimes it's worth 3 or 4 marks. Sometimes it's worth more. But again, there could be 7 or 8 marks. And we're looking at about 8 marks for a grade boundary here. So if they go big on binary and you've learnt these systems, you're absolutely laughing. Okay, next we're going to go to hex now. Before we jump into hex, just cast your mind on these figures here. And I challenge you, as you're listening to me talking, to particularly have a look, at this column here. This is how you count to 20 in binary. Now, just to be clear, you'll get no marks in the exam for counting to 20 in binary. But if you know how to do it and you're quite confident with it, suddenly a lot of mysteries vanish very, very quickly. So with binary, if you look at the very start of it, the first number is 01, not 01, it is 01, okay? But look how this fills out here from the left, 01, 10. See how this very end one changes each time, 01, 01, 01. So it's simply working its way from the right-hand side, and the numbers are filling in where they naturally have to. And there comes a point where the numbers have to get bigger. So once you go to 01, 10 and 11, well, you have to add more numbers, don't you? So you simply go from 11 to 100, 101. You will find that if you actually look at this for about 3 minutes, you'll suddenly go, oh, I see, that's how it works. It's only because we're so conditioned to doing it with decimal that we look at hex and go, well, that's just weird, that's just crazy, why would you do that? But when you look at it for a while, it's just another number system. There was a primary school teacher getting very frustrated with all of us when we were trying to count to 10 and leaving out 4s and not going to 10 and starting to 10 and then starting at 1 again, because we literally had to have this sort of forced into us. So binary is quite easy to pick up, but you might find that a lot more helpful. Okay, over to the right-hand side here, and that is the hexadecimal 1 to 9 and then A, B, C, D, E, F. And the point I was making earlier is this here, right? 10, that means that it's 116, because look, it's gone 1, 2, 3, 4, 5, 6, 7, 8, 9 down to here. And then it's gone A, which is 10, and then it's gone B, which is 11, C, which is 12, D, which is 13, E, which is 14, and F, which is 15. So once it goes to 10, it's got 116. So that's 116 and no units. So that's 16. 1, 1 is 17. 1, 2 is 18. Again, it's odd, it's weird, it's strange because we don't use it. But it's just another counting system. So it's actually worth familiarising yourself a little bit with that, because then it's so much easier to do the maths. And again, the good mathematicians can probably work it out inside their heads, but there's no need to. And I'll show you the system for doing this right now. Right, so this diagram on the board here really demonstrates that if you have to turn things to and from hex, you're going to need to use binary. So I've already shown you how to do this step here, okay? I've shown you how to get from denary to binary, which was draw the grid, fill the numbers in, or ask yourself what's the biggest grid number that goes into your decimal number once, okay? So we've done that. But then what you need to do is this second part, which is if you're going from decimal, denary, to hex, turn it into binary, and then turn it into hex, okay? So I'm going to show you these conversions now. And again, they're actually quite straightforward. The maths involved here is remarkably simple. Right, so we're now going to look at this one here, which is converting hexadecimal, so base 16 numbers, into denary, into decimal, into our number system, right? So we're going from hex to denary. Now notice, I'm going to go back a slide here, that if we're going from a hex to denary, there's hex and there's denary. So we first of all got to turn it into binary, and then we know where we are, and we can turn it back to decimal, to denary, okay? That is our job here. People are turning up. Hello, guys. Welcome. Do introduce yourselves. Don't be shy. All right, hex to denary. If you notice, we've done units, right? So we know that where you've got 1, 2, 3, 4, right? 4 bits make a nibble, yeah? And these 8 bits altogether would make a byte. So we've broken our hex number, and this hex number is the 5, which means 5 times 16, 5 sets of 16s, and then an F. What's F in hex? So we've got A is 11, B is 10, and so on. So you do need to know that F has got its own number value. So you need to go away and work those out and make sure you're happy. But that's the only difficulty you've got. So now let's do, and it's the same process we've done here before, is that you create 2 nibble tables, 1, 2, 4, 8, and then 1, 2, 4, 8. So these 2 tables are identical, and you're drawing out 1 table for each number, okay? So the F and the 5, and as you can see by the arrows here, the 5 relates to this nibble table, and the F relates to that one, okay? So you simply fill out the grid like so, 1, 2, 4, 8, 1, 2, 4, 8, and then you ask yourself the question down here, what is the biggest grid number that goes into our number? Well, 4 goes into 5. This is where I'm looking here. This 4, get off. This 4 goes into 5 once, so that's why I've put a 1 there. And what's left over? 1 is left over. What's the biggest number that goes into 1? 1. And we've resolved that. So then look at the right-hand side. So let's get rid of this. Have a look at the right-hand side. We're then going to look at F. Well, you should have worked out by now that F is 15. What's the biggest number that goes into 15? Why, that is 8, okay? 8's the biggest number that goes into 15. Let me try and get hold of that here. There we go. 8's the biggest number that goes into 15. Just there, okay? 8 goes into 15. There's 7 left over. What's the biggest number that goes into 7? It's 4. There's 3 left over. This is quite tedious, isn't it? What's the biggest number that goes into 3? It's 2, with 1 left over, and that's the one there. And it's no surprise that in a nibble table, which can only hold 15 values, this is where we find ourselves. An 8 plus 4 plus 2 plus 1. 1 byte, 2 byte, 3 byte, 4 bytes. Okay? So that's how that works. That's the first part, is you've done your tables. This all sounds very complicated, but if you go back through it and look at the process, it's exactly what you've done before. The only slight weirdness is that you're dealing with Fs, but no Gs. No Gs in hex. Right, so you've done that. The next thing is you smash. So going back, there are our 2 nibble tables. 0101 1111. And all you do the next step is you smash that together, okay? And you turn it into our old table that we're used to. 1, 2, 4, 8, 16, 32, 64, 128. And then you do what we've done before, and you convert it into denary that way. So you just do some simple maths, which is we look down to see where we've got ones. So there's a 1 by 64, a 1 by 16, a 1 by 8, a 1 by 4, 1 by 2, 1 by 1. And you simply add those all together. So 64 plus 16, 64 and 6 is 70, plus 10 is 80, plus 8 is 88, plus 4 is 92, 94, 95. There we go. Happy, happy? And again, you've got time to actually work this out on paper. But do a few examples, but this will be in the exam. And it's a series of steps that you've got to follow. Once you've drawn the table out, the rest of it's quite easy. It's just some simple maths. And it's not even particularly stretching in terms of the subtraction that you have to do. But you've got time to work it out if you want to do it on paper. All right, that tells us the same thing. Now we go to this one, binary addition. I know that I say that everything's easy, but honestly, trust me, the only thing that you need to know to do binary addition are these facts on the right-hand side here. And even if binary makes no sense to you and you think it's ridiculous and you wish to go on strike, all you need to know are those 4 facts on the left-hand side there. And I would say the first 3 are facts that you'd probably willingly accept, regardless of any other thing you may have ever thought in your life. And that is that, back to here. And that is that, for example, first of all, 0 plus 0 is 0. 0 plus 1 is 1. Again, nothing contentious at all so far. 1 plus 0 is 1. Equally, no problem. But then we do get into binary land, where 1 plus 1 is not 2, because they haven't got any 2s, so it's 1, 0. So you need to know that fact. And 1 plus 1 plus 1, well, think about it. What can it be? 1, 1, because the 0's got to increase. We've got 11 people here. Excellent. Very, very good. If you can literally have this mantra running in your head, 1 plus 1 is 1, 0, 1 plus 1 is 1, 0, that is literally all that you need to do this. So I'm now going to go over to the right-hand side here and look at this binary addition. So in this instance, we have taken this number and we're going to add it to this number here. Got it? I've pre-worked it out, but I'll go through it from right to left so that you are happy with it. So I'm going to start with, on the right-hand side there, 0 plus 0, again, Sherlock Holmes didn't apply here, is 0. Nice, easy start. Then it gets a bit nasty. 1 plus 1. Let's go to our cheat sheet. 1 plus 1 is 1, 0. So therefore, you put the 0 down just here, and you carry the 1. All right? And there's our 1 carried down here. Let's go back to our plan. 0 plus 0 is 0, plus the 1 we carried is 1. So we write the 1 in here. So far, so good. We're resolving this quite nicely. Let's try this next one. 1 plus 1, let's go to the cheat sheet. 1 plus 1, it's still 1, 0, which is helpful. It never changes. 1 plus 1 is 1, 0. So therefore, you put the 0 down here, and you carry the 1. Next, 1 plus 0 is 1. But you add the 1, and that's 1 plus 1, which is, I'll stop repeating the same thing again. Do you see what I mean? 1, 0. So therefore, you simply put down the 1, okay? 1 plus 1 is 1, 0. 0 down, carry the 1 over here. And then you do the same thing. 1 plus 0 is 1, plus 1 is 1, 0. And that's the 1, 0 to finish it off here. I would spend a bit of time looking at that and just going through it. But I promise you, this is so simple once you bear in mind these incontrovertible facts here. 1 plus 1 is 1, 0. 1 plus 1 plus 1 is 1, 1. And you're never going to have to do more than that. So as long as you follow this pattern, work right to left, and do it as you do addition with denary, it's dead easy. If you've got any questions, guys, just ask me, okay? Just ask me. We've still got 10 people here, which is excellent. Right. Next, binary shift. Where are we time-wise? 35. Okay, we're doing well. Binary shifts. Again, I know I say everything's easy, but this is remarkably simple, and it just involves adding or taking away zeros. The hard thing is to get your head around what binary shifts actually are, or the harder thing. And the first most obvious thing to say to you is shifting means moving something. So, yeah, a shift means movement. So why do processors do binary shifts? This would happen inside the arithmetic logic unit, which of course has the accumulator, the ACC, as its memory register. So it's a quick way for the CPU to be able to multiply and divide binary numbers. And this is how it works. Obviously, it's binary. So when it multiplies and divides, it can only multiply and divide in binary steps, which means that it can multiply and divide in 2 or 4 or 8 or 16 or 32 or 64. And each of these is called a step or a place. Now, next step. So you're happy so far? This tool allows you to multiply or divide your number by 2, 4, 8, 16, 32, 64. Okay? There we go. That is fact number 1. Fact number 2 is that it doubles each time. So if you go one place, it's by 2. 2 places is by 4. So if you shift 2 places or shift 2 bits, they sometimes call it, which means you move 1 place to the right or 2 places to the right or 2 to the left. So you can shift left and you can shift right. And we'll come on to which is multiplying and which is dividing in a second. When you move your number left or right, you're either going to lose bits and then you're going to add some bits on somewhere else, okay? All right? But when you move one place, which I'm going to go back to here because it's worth spending a little bit of time on this, if you move one place, you're either halving or doubling the number. If you move 2 places, you're either dividing the number by 4 or multiplying it by 4. If you go 3 places, you're either dividing it by 8 or multiplying it by 8. So that is what binary shifts do. So here's the trick. If they say what happens if you do a left shift 2 places, well, you know that 2 places means that it's going to be either being divided by or being multiplied by 4. Right. So that is the takeaway from that graphic. I hope that makes some kind of sense to you. We've got 8 people on, which is excellent. Left shift. So left. Right is to multiply. Left shift is to divide. Okay. Sorry, right shift. I've got it wrong way around. Right to divide, right shift to divide, left shift to multiply. Okay, that's what it is, which is why it works this way. So this is left shifting. So let's the description that I can give you is that it shifts all the digits in your. So imagine we've got this one here, right? This number here. We'll start down here. 1100. If they asked you to perform a shift 4 places, a binary shift 4 places to the left, you would end up with this value here. And the keen-eyed among you will say, well, hang on, that's exactly the same number, except they've stuck 4 zeros at the end of it. Yeah, that's it. So when you do a binary shift left, if they say 4 places, you add 4 zeros to the right-hand side of your number. If it's 3 places, you add 3 zeros. If it's 2 places, you add 2, and so on, okay? It's literally that simple. So you've simply got, so we say you move the number. You don't. You just write a 0 on the right-hand side of it. So, and that's the thing that you need to remember. So you shift left to multiply and right to divide, okay? Left to multiply, right to divide. So if you look at this, 1100 over here, the denary value in decimal is 12. You do a 1-place shift and it becomes 24. You do a 2-place shift, it becomes 48. See how this number here is doubling each time? So it's a really quick way of multiplying. You're just sticking zeros on, okay? So when you think about it, we do that all the time in denary, don't we? If you want to multiply it by 10 and multiply it by 100, we just stick extra zeros on the end. So that is literally all that's happening here. So the only thing you've got to remember is that when you want to multiply, you shift left. All right? So that is that one. Let's now go on and look at the next one, which is a right shift. Now, there is a slight complication with right shifting, is that it's not that accurate, or it may not be that accurate. Work this through, right? So we're doing the same thing, except this time we are starting over on the left-hand side because we're shifting right. And there's our number. So you in the exam, they might give you that number and they'll say, perform a two-place binary shift to the right on 100,100. So therefore, you would then go from 100,100 to 1001. So what's happened? Well, we can work this back, because if we look at 100,100, becomes 10010. So they've taken a zero away from the right-hand side. So that is simply all that you are doing, is that you are getting rid of the last digit. And if they say do a one-place shift, you're getting rid of the last one digit. If they say do a two-place shift down here, you're getting rid of two digits. A three-place shift, if you get rid of three digits of this, if you get rid of these three digits and get rid of those, that leaves you with 100, okay? And not 100, 100, because it's binary. So don't say 100. But here's the problem, right? Is that if you were to run this through in denary, we go from 36 here, we go to 18, no problems, because that's half. We go to 9, no problems. But now we do have a problem, because binary, you can't do fractions in binary. So half of 9 actually is going to be 4 doing it this way, rather than 4.5, because half of 9 is 4.5. So at this point, you can see here, we lose accuracy. So they sometimes say, what's the impact of doing a binary shift right? Losing accuracy, okay? You just lose accuracy. It's close. So rather than ending up with 4.5, and then 2.25 here, you end up with a number which isn't quite accurate. So that is your right shifting. I hope that makes sense to you. Again, look back at that, because it'll be in the exam, and it's not a difficult thing to do. I tend to remember it myself by thinking of a king who's saying, it is my right to divide the people. For some reason, that's the way I've always remembered it. It makes no sense at all, but kings would say things like, it's my right to divide. And there we go, now I've given it to you. So once you know that it's right to divide, you know that it's left to multiply. Boom. So that is your binary shifting all done and dusted. That's the description in words. Right shift is division, left shift multiplication. The leftmost bit is discarded, and the rightmost bit is discarded. So it's whether you're going to get rid of the data on the left or the right, and how many numbers, how many places you're going to get rid of, you're going to delete, okay? And do you add zeros back to the other side? That's it. So that's your binary shifting. Do some practice on that. There'll be loads of examples online where you can practice that. And I know that your teacher will have some examples for you. Where are we? 43. Characters. This is the last thing I'm going to cover today. Well done, the 12 of you that are still here. Right. This first thing here appears over and over and over and over and over and over again in your syllabus. All characters are represented by a binary number. Okay? That keeps appearing. Not just all characters, but images are represented by binary numbers. It's because it's pixels, and each pixel has its own binary number, which is its color. Okay? So then the first question for this will be, what is a character set? And you need to say this sentence. A character set is a set of characters the computer can understand. Bing! That is literally in every single mark scheme. What's a character set? A set of characters the computer can understand. So make sure you know that, okay? Right. So a character set is a table, if you like, where you've got all of the different characters mapped out. Now, the first character set that came out was one that's called ASCII. That's this one here. And it was an 8-bit character set, okay? The problem with having 8 bits is that you could only store 256 codes, because if you count up an 8-bit number, and you've only got it's 8 bits. 1 is 256 in denary. So you've only got that number of characters that you can play with. The problem with ASCII is that it's fine for doing English, because all you need is A to Z capitals, A to Z lowercase. You need the numbers. You need the special characters like the space bar, the escape key, the tab, commas, punctuation, a few other things, but shift, alt, all of that sort of stuff. But there's more than enough left over to do it that way. So ASCII is actually quite useful, because in ASCII, each character, whether it's an A, a B, or a C, is represented by 1 byte, okay? However, the problem with ASCII is that if you write in Japanese or Chinese or Korean or Greek or Russian, then your alphabet doesn't work, because there aren't enough characters to represent all of the different characters for those languages. So therefore, they created a more recent character set called Unicode. And Unicode, rather than being 8-bit like ASCII, is 32-bit. 4, 8 to 32. So you've got significantly more characters that you can represent. And so this is the detail here. These are just facts, right? Is that while in ASCII, each character, so the A will be represented by 1 byte, okay? Not a bit, a byte, 8 bits, okay? So 8 bits, 1 byte per character. So an A is represented by a number which is 8 bits, or 1 byte. Whereas in Unicode, it's a 32-bit number, and it means you've got 4 bytes per character. So it's more memory intensive. It takes up more memory, but it means that you can represent over 4 million characters, which is more than enough for any language, every language on planet Earth, plus any that might get written over the next 1,000 years. Okay, so Unicode is the one that is generally used. But that's the key with character sets. And you know what? Honestly, this question here, this statement, it's always worth a mark. And they might in the exam get you to riff about, what are the benefits of using ASCII? Well, ASCII is an 8-bit character set where each character is represented by 1 byte, and it can represent up to 256 characters. But Unicode, on the other hand, although it's a 32-bit character set, you can represent over 4 million characters, which means that any foreign languages, in any languages, you can represent their characters as well. So that is your kind of character set. It's all the information you need, really. Right. Okay. So now this one, again, they didn't get you to do this in the last exam, and it was calculating the size of text files. And there's a wonderful logic about this, which is that in the question, they will at some point tell you how many bits per character. In other words, is this, going back to, let's get rid of you, going back to here, is it ASCII with 1 byte per character, which is 8 bits, or is it 4 bytes per character, 4 times 8, 32 bits, okay? 8 bits or 32 bits per character. So that information they'll give you, and then it's just some simple maths after that. And then how many characters, okay? So if there's 1,000 characters, you need to know how many characters there are and how many and what character set is being used, and then you've just got to do some maths. Really, really simple, okay? So calculating file sizes, and I will next week do that on image and sound as well, okay? I'm getting a bit hoarse now. Right, question for you, quiz time. Let's run the music and see if you can do some of these. There are still enough of you here to answer this. Any ideas? Doing a logical shift left does what to a binary number? Any ideas? Any ideas? Anyone brave enough to say? I can see that the answer is no. All right. I'll push on to the next question. I'll do a few of these. Okay. The next one's this. It was multiply. Do you remember right to divide? So if you go left, you multiply. What about this one? Doing a 2-bit left logical shift has what effect? Has what effect? Any ideas? Are you guys able to comment? We had a few commenting last week. What about a 2-bit left logical shift? Don't get drawn into that when they say 2-bit, you think, oh, that's either dividing and multiplied by 2. It's not. A 1 shift would do it by 2. A 2 shift would do it by 4. So a 2-bit has to be 4. 1 bit is 2, 2-bit is 4. 3-bit is what? Is 8. So then we've got 2-bit, which is going to be 4, and a left logical shift, if it's right to divide, it's left to multiply. So you're left with multiplies by 4. Notice that they suddenly say, what is the effect? The effect is to say that it multiplies or it divides it by. There's a difference in the question, what's the effect of doing it, to actually work out the answer, or, what is the result of doing it? Okay, there's a difference, effect versus result. What about this one? So there's the question, 1000, 1100. Which answer has correctly applied a 1-bit left logical shift? Right to divide, left to multiply. So what has happened here? Well, I shall break it to you very gently that it is that one there, okay? All right. I think that I am going to bring this to an end, but I will leave your teacher, Mr. Godfrey, with these quizzes so that he can quiz you on it. Okay, guys. So I'm going to whiz through until the very end. Boom, 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 boom. I'm going to go through to here. Yeah, revision ideas. So here are some ideas for what you could do to get yourself ready for next week and to make sure that you're happy with all the areas that we've covered. Practice some conversions between binary and hex, going both ways, okay? And practice different conversions each time. Don't do the same one because then you cheat yourself if you know the answer. Be confident with your answer in why binary. Why do computers use binary? Because computers use circuit boards. Circuit boards have 2 states, on and off, electricity flowing, electricity not flowing, and that's represented easily in binary that also has 2 states, 1 and 0. Okay? You didn't say all of those things. As long as you're saying one of those, you'll get a mark. Okay, this I just talked about, right? The difference between effect and perform in binary shifts. So the effect of a binary shift would be that the numbers being multiplied or divided by 246, but by 248, 16, 32. The perform would actually be what is the answer when you do this binary shift. Okay, so that's the key words there in the exam. So learn the fixed size of storage media. So for example, how much can a CD hold? 740 meg. Roughly, what can a solid state hard drive hold? Roughly, what could a DVD hold? And so on, okay? I fancy they're going to make you do some conversions, sort of upscaling and downscaling bits, bytes, megabytes, kilobytes, and so on, and then say which media would you recommend for it. So you'll do a bit of maths involving 8 or thousands, and then which medium would you recommend? And you'd say, well, I would go for Blu-ray because that can hold 50 gig, and that's inexpensive, although it is easy to damage. But as long as you look after it, it's not that robust. I mean, then we've got our Polish crayon-speaking Polish during role play. It brings all of that in, which are our characteristics of storage. Okay, all right. Go back and look at the steps of binary addition, and that mantra that I kept saying: 1 plus 0. Okay, 0 plus 1. 1 plus 1 is 1, 0. 1 plus 1 plus 1 is 1, 1. Really important, okay? For next week, when I put up that question on the register of the CPU, we had success this time because one person got it right, and that was you, Connor, so outstanding. And you could have had memory data register, okay? The MDR is called, that one. And then we've got the retrospective revision planner, which you should be receiving at some point. Don't forget to have a look at the specification to make sure you're happy with what you're doing. Guys, it's 5-2. You've done very well. Next time, images and sound. We're also going to look at compression as well, okay? So that will be this time next week during your half term. No sleeping for computer scientists. Guys, I wish you a peaceful week, and I will see you again in a week's time. Bye-bye. Cheerio.